So Monte Carlo, there's a section in this chapter at the end which is not on the exam that deals with American options, but your intuition would be an American option is going to be far more difficult to deal with, because when you're with a European option, we're at expiry, it's a simple decision. If the stock price is in the money, I exercise. If it's not in the money, I don't. Nothing could be simpler. If I'm dealing with an American option, I indeed have to generate a path of stock prices, because it's not just a question of expiry prices, but the decision to exercise is complicated for an American option. If all I know is the stock price today, I really can't determine whether I exercise or not. Because if I exercise today, I'm giving up the opportunity to exercise in the future. So in a sense, to evaluate an American option using a Monte Carlo method means that you somehow have an efficient way at any point along the path of prices to determine not only the exercise value at that time, but what's the value of future exercise. And you may recall this idea is explicitly implemented in your binomial lattice evaluation of American options. Recall what we did. At each node of the lattice, we compared the exercise value of the option to the expected present value of future exercise, and we chose the larger of the two. What we were doing is saying, if the value of exercise today is bigger, that's the value of the option. And in fact, I would indeed exercise. If the value of future exercise through the expected present value calculation, if that's bigger than current exercise, that becomes the value of the option at the node. But what that calculation told you is you would not exercise then. Even though the option might have been in the money, the value of future exercise exceeded the value of current exercise. So consequently, when you're dealing with an American option, it's quite complex, because you have to figure out how to determine the value of future exercise, which is not readily at hand in this methodology. There's also a question of efficiency. I wouldn't say it's inefficient or efficient. What is true is that sigma n in this formula represents the standard deviation of the price estimate using n stock prices. Sigma c is the standard deviation of the individual exercise values. So if I look at the standard deviation, so let's imagine that sigma c, c is the standard deviation of individual exercises. Namely, imagine that if I went back to the 2,500 prices I generated and took each one of them separately and created a present value of that payoff. Sigma c is the standard deviation of those payoffs. So if I look at, and of course there are many zeros, there are some large payoffs, sigma c is the standard deviation of the collection of discounted payoffs. And in our example, it turned out to be a little over $4. Well, the price we're estimating is, in fact, an average of those payoffs. So the standard deviation of an average is the original standard deviation divided by square root of n. So you can see that in each one of these, that the error, with 2,500 observations, it's telling us that the standard deviation is about 8 cents. So you could construct confidence intervals in the usual way using a student t or a normal distribution. The central limit theorem would basically tell us that the distribution of values that we would produce for a stock price, for this option price, is approximately normally distributed, and we see it has a standard deviation of about 8 cents. So we're getting a pretty good estimate with 2,500. If we went up to 21,000 observations, we would have a standard deviation of a little under 3 cents. So you can do some statistics to not only in these methodologies determine an estimate of the price, but you can also, by calculating the sigma c, the variability of the individual payoffs, you can estimate what's the standard error of the price estimate of your option. And you can see it goes with square root of n. I think the author's term of inefficient means that you have to quadruple your sample size to cut your standard deviation in half. It would be nicer if we had a procedure that was proportional to 1 over n. Then we could double our sample size to half the error. So here it's inefficient in that way. We have to quadruple n, and that cuts our standard deviation in half.